Fragmentation is a very interesting topic to me, specifically that it is a very overloaded term because now when I say fragmentation, do I mean disk fragmentation? If you grew up in the 90s, you've probably seen, hard drives and options in the OS to defragment your drive. I'm not really talking about that per se, nor that I'm talking about fragmentation at layer 3 on the IP packet, where if an IP packet that is of size, I don't know, 1500 bytes encountered a router with a smaller MTU, maximum transfer unit, for any reason, then the router will chop that large IP packet into a smaller, what we call fragments, based on the offset of where the bytes are. I'm not talking about that type of fragmentation. I'm talking about fragmentation in memory. And I'm working on a new course, an operating system course, and that's where things for me started to ignite more interest, because how critical is fragmentation in memory? I want to answer a few questions in this podcast. Like, what is the fragmentation in memory? What is external fragmentation? What is internal fragmentation? And is it really? That's the most question that I can't find answered in the internet. I actually did find one article from Yale from 2010 that actually discusses this exact topic. And the question is, if I put my data, right, in different places in RAM, is there a cost for reading a block of memory that, let's say, an array that I know is contiguous, but it is physically not contiguous on the RAM, right? It is chopped off and placed in multiple physical location, different rows and columns in the DDR RAM. Is there a cost to reading that and jumping between one place in memory to another place? That's the question I'm trying to answer. And I think I'm 99% there. How about we jump into it and discuss this? Welcome to the Back Engineering Show with your host, Hussein Nasser. And today's topic is fragmentation in memory. You see, when I allocate a certain memory, my process says, hey, I want 1,000 bytes. And I want this necessarily, memory is always contiguous next to each other. That's the rule. Right? Now, when I say contiguous in memory, virtual memory kind of breaks this rule, because it can present you with 1,000 bytes that is contiguous from byte 0 to byte 999, but it can play tricks on the back end, no pun intended, that it will swizzle that. It will trick you. It says, all right, yeah, virtually you have 1,000 contiguous, but physically they are all over the place for one reason or another. I don't have memory. My memory is fragmented, which I'll come to, and it's over all the place. So that the contiguous memory is a rule that comes to the operating to the process itself, to the request. But implementation can differ. So now if I say, hey, give me this 1,000 memory, allocation of this memory is critical. Throwing all the rules out of the door, how would you implement such strategy to allocate memory? Well, you really have one option is allocate exactly the amount of memory that the client asked you. And when I say client here, I mean the process or the thread of execution, right? And it's asking basically what? The kernel to allocate the memory, right? The operating system to allocate this memory for you, right? And you can abstract this idea to anything, really. You can build your own memory management system, and you have a client and a backend, and the client requests memory through a HTTP request, right? That's fine, like Redis. Hey, I'll allocate this memory for me, right? And that's the idea. There is a client that requests certain memory, and then you can. So this is the first approach. Give me exactly what I asked for. I asked for 1,000, give me exactly 1,000. I asked for 10 kilobyte, give me exactly 10 kilobyte. 1 megabyte, give me exactly 1 megabyte. What's wrong with this approach? Well, this approach is efficient because you're exactly given what you're asked for. But I want you to imagine, fast forward through the just play it out. Imagine thousands of processes, one requesting 3 bytes, one requesting 10 bytes, one requested 1 megabyte, one requested 10 megabytes, one requesting 10 kilobytes. And there's this the memory will be allocated in order, whatever, first come, first serve, in the order that comes in. And then eventually processes will terminate and they will deallocate. So what will happen is the 3 byte process will deallocate, the 10 kilobyte process will deallocate, the 10 megabyte maybe lives a little bit longer, the 10 bytes will live a little bit longer. And what will happen eventually is like this nice used memory, all of a sudden now will have patches in the middle, right? It's like, oh, there's like a 3 bytes. Free memory now. Oh, now it has like a 1 byte here. Oh, there is like a 10 kilobyte here. Oh, there is like 1 kilobyte here. And you will have these patches in the middle, right? And these patches, unfortunately, are very, very tedious. Because what are you gonna do with this 3 byte patch that is a free memory? The possibility that another process will ask for a 3 byte is so low that this 3 byte will remain 3 byte, unallocated, absolutely useless in the middle of your memory. Yucks, right? And that's what we call external fragmentation. Because looking externally, right, you have memory, right? But they are all over the place. Like, oh, you have 10 bytes here, 5 bytes here, 10 bytes here. And so if someone genuinely, let's say like you filled up all this RAM, right? And someone wants a 1 megabyte. Guess what? You absolutely have 1 megabyte. You actually have maybe 20 or 30 or 40 megabytes. But guess what? You don't have 1 megabyte of contiguous memory anymore. You don't have that. Because it's all over the place, right? So you cannot allocate memory with this approach because it's all over the place. Now, virtual memory actually solves this problem, right? But we're going to come to that in a way that it doesn't really use this approach, this on-demand dynamic allocation is frowned upon because it's unpredictable, right? So that's the problem with external fragmentation. You have memory, but you cannot possibly allocate it. Let's say you cannot easily allocate memory. So what people did is, all right, we're gonna solve this problem in 2 ways, right? First of all, there's this monkey business that you can. If you ask me for 1,000, I'm not going to give you 1,000. I'm going to give you a fixed block. And it may be more than what you need. It's almost always more than what you need, right? So if let's say my fixed block size is 1,000 bytes, or 1,024. If you ask for 1,000, I'm going to give you that one block. If you ask for 1,001, I'm going to give you 2 blocks. One block you're going to probably use all. The second block you're going to only use 1 byte. And you're going to have 999 empty space. Now you just you just created another problem. And this is the this is the life that we're living currently, right? Human beings, everything we solve, we always create other problems. Always, always, always. There is no exception to this. Everything you create, there is always a side effect to it. To everything. You can think of anything, there is always a side effect, right? And I'm not gonna philosophize here, but just think about it a little bit. It's very interesting if you think about it. So now you have another problem where you created something called internal fragmentation. Now you have a space, but guess what? You as the operating system, you have no control because you gave this block, this guy, something that more than what they need. Now, what you got as a result, as a side effect of this, is a nice block sizes. So if I deallocated something, I have fixed size of memory. So these patches still exist, but they are more manageable and they're more useful. Right? Furthermore, virtual memory can actually thrive here. Now I can create a mapping table that says, hey, this block, you allocated this block as a logical block, but physically it's this block. And you create a mapping table, what we call the page table, right? And with virtual memory, now you can allocate certain amount of memory, even if it's not contiguous. You say, hey, I want 10 megabytes. And of course, virtually, I'm going to give you a virtual address that looks contiguous from 0 to whatever, 10,000. But I don't have that. I don't have the luxury to give you all of that in one contiguous physically, right? In the RAM, they are not physical. I have a free block over here. I have 2 free blocks over here. I have 10 free blocks over here. And then what we do is we fill up these blocks. So it's all right. Block number 1 logically is actually physical block number 917. Block number 2 is block 10,001 and 10,002. And this block is this block. And then you start mapping it. Very, very creative. You know, virtual memory is a beautiful design indeed. You know, there's of course a cost that comes with it, and we'll come to that. So now you filled up, you technically solved external fragmentation. Remember, what was the problem with external fragmentation? We have a space, but we absolutely have no way to fill up these gaps in the middle, these patches. I cannot use them. Well, with fixed block size and paging, essentially, and, you know, virtual memory, of course, you have to virtualize things. Now you can fill up these gaps. You can reuse these gaps. Very nice, right? Furthermore, with my favorite word today is furthermore. So moreover, let's change it a little bit. What you do is, even if you don't have space, because now you have this physical block that is just well known, well defined, I can swap it back to disk. Say, hey, you've been consuming this memory, but you don't really use it much, huh? I know you need it in the future, but I'm gonna save it to disk in a swap area. Here's a space in disk. I'm gonna write it back here. I'm gonna remember that you need those. This is in your virtual memory table, the page table. I'm gonna point to that swap space. Like, hey, if you ever need it, it's right there, okay? But that physical space is released for other more important, you know, urgent processes that need memory. And then you the next time you access it, it's like, wait a minute, where's my mapping? You'll say, oh, there is no mapping anymore. There is no physical block that maps to my virtual block. So you would detect it. Oh, someone swapped this to disk. Page fault. That's what's called page fault. And then things happen and you read it back. Well, you don't do anything as a process. It's just the operating system does all that. And then read it back and then just put it. And it does not put it back in the same physical space. No, no, no. You don't care, right? It's going to put it somewhere else and update the mapping table to point to these new physical pages. Very beautiful design indeed. I absolutely love it. Now, it does, however, solve external fragmentation. We don't have that problem anymore, right? But we do have a problem with internal fragmentation. Now, the page size actually matters. Like, how much do you allocate? What is this fixed size thing that you're talking about? Is it 4 kilobyte? That's the default, by the way, 4 kilobyte. Well, if I allocate 4 kilobyte and my processes are really efficient and only use like few bytes, like, hey, I just need a few bytes here, 3 bytes here, right? And operating systems are pretty smart. Like if you allocate 3 and then you allocate another 3 bytes and allocate 5 bytes, it's gonna still reuse the same block of memory. It's not gonna like allocate a whole brand new block for you, right? So they're smart. But still, some processes are not hungry and they're not, as we say in Arabic, sharih, you know? There's no affinity in these processes. So they use global memory. So larger block size, they call huge pages, you know, increase internal fragmentation. On the opposite side, you know, database systems, I would say, will benefit with larger memory page sizes, you know, huge pages. No, I can't remember what's the huge page size. Not 4 kilobytes, more than that. It's like, could be a meg if I'm not mistaken. All right. So because database systems, like most of the database system is caching, right? I'm gonna allocate like all these shared buffers and put it in memory. Okay? I don't want to allocate like small tiny blocks. There's a lot of management and mapping and there's all stuff. I don't want any of this. I want just like massive, huge, nice chunk of page. Give me map. So the mapping records decrease, right? The mapping table will decrease naturally. But that's not our topic. Our topic is internal fragmentation. So now the more the page size, the more these gaps inside the page will be wasted. And there is absolutely no way the operating system knows that, oh, you only use 10 of this. Maybe there is, but most of the time it's like, hey, I allocated this for you. Maybe in the future you're going to use it. So the OS is not going to touch it. So chances with paging, we increase the fragmentation as well, but it's internal. It's internal to this block, this black box that we allocated. Internally, there is fragments all over the place, but it's internal. Now, memcached is beautifully solved this problem. Fantastically solved this problem, memcached. No? Who created memcached? Was it Facebook, right? This Zuckerberg guy. No? When he doesn't do all this monkey business with what is it called, this Web3 or this VR stuff, he actually designed really good systems. But now he's just off doing all this, weird things. No? But yeah, so what they did is they created this idea of slabs, and they broke down the slabs into smaller and smaller memory. So now they basically outsourced the idea of memory management completely to a low level, such that even if you have internal fragmentation, you don't have that problem anymore because they manage objects in its smaller forms, and they have like different size of chunks. I believe they call it. And if you release something, they release that object, but it's still allocated to the operating system. That memcached just allocated the whole thing, but the memcached as a software broke down all this memory allocation and assigned it state, if you will. So this object is allocated. I made a whole course about memcached if you're interested. It's also on the free code camp website. Go check it out. But yeah, very brilliant design. So they solved internal fragmentation at the application level. So that's very interesting. But now let's come to the final question, which is the cost of virtual memory, you know, especially by solving external fragmentation, by having us map through different location physically. I allocate an array, I allocate a slab of memory, 1,000 bytes, but physically they are even maybe in different DIMMs altogether, different DDR RAMs. You know, there's like here and here and here. With time, they are all over the place. Now, to talk about this, we need to talk about how the CPU actually read data from RAM. CPU doesn't really read 1 byte at a time. No. The DDR controller, I'm talking about, like, you know, double data rate RAM. This is the final, you know, the latest and greatest technology, DDR5. The minimum thing you can read is 64 bytes. You know, you make a request, you want to read an instruction from memory, or you want to read 1 byte out of specific address of a physical address. No way you can get 1 byte. It's a waste of time to get 1 byte. The minimum you can get is 64. You can get more if you want, but 64 is what you get. Just like it, 64 bytes. And that matches nicely the cache line on the L1 cache on the CPU core itself. So you read 64 byte. So guess what now? Now back to our beautiful caching. We are back in engineering. We know this stuff, you know? If I read something and I ask for the first byte, you know, and I got 64 bytes, then the next thing that I want to read is actually next to it, is actually physically next to it, the next byte. Guess what? It's in the L1 cache. Beautiful. 5 nanoseconds. Very fast. But that 64 byte fetch from memory, that's a, what, 100 nanosecond, I think? 50 to 100 nanoseconds? I know it's 100 nanoseconds, it's still fast. But on the grand scheme of things, it's, you know, it takes ages to read that 100 nanosecond. So now, imagine this. And that 100 nanosecond is literally the most, the cost of it is to open what is called the row in the DDR RAM. You know, a row, this is how our RAM is consisting of. There is the bank, right? I think it's called the bank. There's the rank, and then there is rows and columns. That's what RAMs are consisting of, you know? And a row have around about 1,024 columns on average, you know? And when you actually want to read, and the column actually has the value, and each column will have, I think, 64 bit, you know, which is what, 8 bytes. Each column has 8 bytes, 8 bytes, 8 bytes, 8 bytes. So technically, modern RAMs, a full row has around 8 kilobytes, you know, 8,000 bytes, no, give or take. That 100 nanosecond that we talked about is the cost of opening that entire row. If you want to take 1 byte or the whole 8,000, you're going to pay the 100 nanosecond cost to open this whole row. And there is electronics that I'm not very, honestly, I'm not very familiar with. But that's the rule here, you know? Opening that row just to read from that, it gives you, like, you get access to a whole 8 kilobytes. And that 8 kilobytes is not sent to the CPU. It's actually put in the row buffer in the RAM itself. It's actually a row buffer in the RAM controller, the memory controller in the DDR RAM. So now you have a cached 8 kilobyte. Think about that. And now you read only 64 byte. Good. That's the minimum. And you use the bytes, use 64 byte. You know, use the next one, and then use the 64 byte. And then until you're done with the 64 byte. All of this nicely cached. You never actually go back to the RAM. But then you say, all right, we talk about contiguous memory, right? If it's everything is physically contiguous, that 8 kilobyte, back to the 8 kilobyte, I want 1,000 bytes that are contiguous. All right, 64, all right, give me the next 64 byte. You sending that request to get the next 64 byte is a signal to the DIMM, no? The dual module, I forgot what it's called. dual inline memory module. And you say, oh, give me the next 64 byte. Guess what? That 100 nanosecond is gone. You don't need to do it because it's cached in the RAM. There is a row buffer with all this beautiful stuff in the same row. You asked for that row. It's the same row. I'm asking for the same row. It's the same address physically located. So now that's a cost. That is like a nanosecond here and there, but no cost. Physical contiguous is a good thing. And you consume the 64 byte, and then you do it again. And you cache it, and you cache it, and you do the next 64 byte. So that's beautiful contiguous memory. Now take the concept of virtual memory, where things is completely scattered. Again, it's the worst case scenario where things are scattered. Not necessarily, but let's take a scenario where my virtual memory looks contiguous to me. Of course, there's the cost of translation between the virtual memory to physical memory and the TLB and all that stuff that I'm not going to talk about. But there's a mapping that needs to be done, and this mapping is done in the, I think it's the page table. It tells you, oh, this RAM, this frame, this block that you reserved actually in this physical memory. So you ask for that address. You take the hit of the 100 nanosecond. And then you consume the 64 byte, and then all of a sudden, your next thing that you need is actually a completely different physical address. You mapped, you change the virtual, memory mapping, and then all of a sudden, oh, this is a completely physical address. It's a completely different place, completely different bank, different complete row, different column altogether. So now what you do is like you send that other request. So, oh, you know what? Never mind. I want this next 64 bit. Where is it? Oh, it's here. Okay, so you send it to the RAM and says, all right, no, you gotta wait, dude. I need to close that old row and open this new row. You just took a hit, another 100 nanosecond. And then you do it again, and after a few reads, maybe you're lucky, everything is contiguous, maybe you're not, and everything is like, it's a different place. Another 100 nanosecond, another 100 nanosecond. Nobody talks about this because it is so minuscule, but I want to shed light on it. It adds up. If you're reading all over data from all over the RAM, physically all over the RAM, I don't care about virtual memory, fragmentation in this case, the cause of external fragmentation, which we solve with virtual memory, created additional degradation, if you will. These 100 nanoseconds. Now you might say, Hussein, you're exaggerating. Not really, because the caches are large. We're going to cache all this stuff. Yeah, I read here. I'm going to take it in the beginning, but then the caches will fill up. We have beautiful large L3 caches, L2 caches, L1 caches. Well, we solve all that. But this comes to the same thing that I'm talking about with backend engineering. We always solve things in I don't know. It's not an elegant solution, We're just ignoring the problem by throwing money at it, Why don't we build efficient software? So now, of course, I'm not proposing any solution. I'm not criticizing anything here. I'm just stating it the way it is. There is cost, and just shedding light on this is so, refreshing. It's a refreshing thing to understand how things work, And we don't really care about this thing anymore because it's so minuscule, but it can add up, Especially it can add up for, large code bases. I know this is still in discussion, but I'm gonna throw it in anyway. MySQL 8 versus MySQL 5. People are still, flabbergasted at why MySQL 8 has huge performance, degradation. There is a lot of regression with 8 compared to 5. It just slow down all of a sudden. And there's one theory that goes on, and we're not going to say 100% that's true, but that's from one MySQL developer, an ex MySQL developer that here's his theory. It says, all right, MySQL 8 added massive code base. They increased the code base, exponentially. There's a lot of lines of code, which essentially, because code lives in memory, right? And if you execute something, says, all right, I want to execute this piece of code. The piece of code lives in memory, right? And lives, well, in virtual memory, okay? Which then the CPU needs, the MMU to be specific in CPU, needs to translate that portion to the physical memory. And that's called a page entry mapping, And that translation is actually, stored, because that translation technically is stored in memory also. It's called the page table. It says, all right, this virtual memory address in this process is actually this physical memory address in this memory, right? And there's like a mapping. This page is this page. This page is this page. It's actually just, it's a very tiny, it's a very efficient way of storing things. They're storing just the numbers. Like, oh, this virtual page, because in virtual space, we're always going from 0 until whatever the number is, 4 GB or even more than that, right? But physical memory is just, it's a one contiguous large thing. For processes, they always start from 0 or 1 or whatever, right? The virtual memory space is identical for all processes, but the mapping is different, and that's what makes virtual memory really attractive. So now back to this MySQL 8, they have like a massive large code bases. Now, if I read this, again, go back to the fragmentation concept, you're reading something, you put it in memory, and then all of a sudden you say, all right, a function call happened. And this function code is a completely 180. It's like that code lives somewhere completely different in memory. Well, you need to fetch that instruction. And that fetching that instruction will require a memory read, which we, of course, hit through the row access in RAM, and you take the 100 nanosecond. And then that function calls another function, and guess what? That function is not next to each other. The code is not next to each other because it's so large, it is scattered all over the space. So what happens is, as you execute code, most of your time is spent, mapping virtual memory to physical, because you're reading the page table, which is in memory, to map, and you're caching those in something called the TLB, the translation look aside buffer, which maps, okay, this is this, this is this, this is this. But that memory, the TLB, is also limited. So as you store more mapping, the old mappings are discarded from the TLB. And you need to kind of invalidate these caches and stuff like that. So you're losing those. If your TLB cache is hit, that's good, because you don't need to go back to memory to read the mapping. But if you miss, there's a TLB miss, then you have to go back to memory, read it, and then perhaps the TLB is full. You have to, it's an LRU. You have to discard the old stuff to make memory for the new one. So you're spending time reading from all over the place and then translating and then executing code. That's one theory. There's a lot of function calls, because we know like inlining kind of help, right? You want, as you execute code, you want the code to be nicely contiguous next to each other, because for the same reasons we talked about memory access, next to each other beautifully. But if you keep like jumping, call printf, printf is all over there, okay, let's go there, fetch that memory, and it's going to be cached, sure. But then if you have a lot of function calls, and those function calls are not next to each other physically, they might be next to each other virtually again, but they are not next to each other physically. And that will cause you, you're reading cache misses, cache eviction, cache. And then you have another problem with multiprocessing, which is like, you have one core, this is another core, this core read something and changed the mapping, and now this core is having the old TLB mapping, so you need to shoot down the old TLB entry and use this new one. So this thing is complex. Operating system, as I make this course, OS is one of the most complex, pieces of software out there. And then this scheduling, then there is process, context switches, and so that's another thing I wanted to discuss. So we talked about fragmentation, and fragmentation in memory. As a summary, there is external fragmentation, where you have space, but they're all over the place, you know. Virtual memory, solve this with paging, which is fixed size allocation. But then you have another problem introduced, which is internal fragmentation. Those blocks, unfortunately, they have spaces. We said, okay, we closed our eyes. It says, okay, I don't care. Who cares? It's just space, you know. But then, even with external fragmentation, we have the problem of fragmented. What looks contiguous to you is actually fragmented in physical memory. And we talked about the cost of retrieving, why did I say it this way? Retrieving contiguous memory from uncontiguous or discontiguous fragmented physical locations. And that has a cost. You know? Just like the whole hard drive thing that when I started this podcast, the hard drive has this needle and it's just moving around from all the spread to read the data, right? That is, of course, way slower. That you're talking milliseconds, right? But now with RAM, you still have the cost, right? With at least the RAM we know it today, you know, is DRAM, right? Is it called DRAM? No, it's DRAM is the synchronous one, the fast one. We're talking about the asynchronous. No, we're talking about synchronous RAM, yes. Synchronous dynamic RAM, which is uses capacitors, which needs refreshing. Okay. Yeah, so I don't know about, to be honest, I don't know about the SSDs. I'm not really well versed about NAND technology in the SSDs. Is this the cost, the same cost? How if I want to read a block in a specific place in the SSD versus at the end, I'm not really traveling per se. I'm sending the request. Even in the RAM, you're not really traveling. Even if you're accessing row 1 and row 1000, it's not about the travel speed. It's about the opening and closing cost, right? We're opening the row, you have to open all the columns. And that takes time to, you know, refresh all the, you know, and do all the RAM-y stuff, you know. But in the NAND technology, it might be different. Is there a cost to, there's other costs to, of course, you know, SSDs and, you know, garbage collection and whatnot. And there's also a mapping in the SSDs to map between, you know, logical block addresses to physical block addresses. But that's not our topic. The fragmentation here in this particular cases, I don't think it's a problem per se in SSDs. Yeah, because there is no this cost of opening something in the NAND, as far as I know. I might be wrong though, but yeah, that's what I wanted to talk about. Fragmentation, very interesting topic, very rarely talked about. So I wanted to throw it in here, and you guys call me out if I said something that you might disagree with, and let's have a discussion. What do you guys think? Let me know in the comment section below. I'm gonna see you in the next one. You guys stay awesome with this net.